Okay, so now I just wanted to show you a little demo. It's called Newton's Cradle right here. And what you do is they're all the same mass right here, and they're all considered elastic collisions. If I were to bring this one up and release it, what happens right here when this thing hits? Well, if they're all adjusted just right, I can see that one off a little bit, but you noticed right here, just one takes off right here. So when I dropped one down right here, what was the momentum just before? It was mv. One took off over here, and that had exactly the same speed, so it was mv. So the momentum before it equaled the momentum afterwards right here. This was an elastic collision right here. Now, suppose I drop two of them down right here. If I drop two of them down, you notice two of them take off right there, right here. So if I drop two of them down, now we have 2 mv, and two of them came up this side, which means we had 2 mv. Momentum was still conserved right here. Now you might ask, why didn't one go up at twice the speed right here? Because if we look at the momentum of this, 1m times 2v is the same as 2m times v. So why not, when I drop 2, why doesn't 1 go up at twice the speed? Well, maybe I haven't done it enough times. Maybe if I do it again. No. 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 It doesn't look like, as many times as I try, I'm never going to see 1 shoot up at twice the speed. And we say, why not? Right here? Well, we said this was an elastic collision. If we were to look at this from an energy point of view, this was a momentum. That's definitely conserved. But from an energy point of view, remember, energy is 1/2 mv squared. This one would have 1/2 2m v squared, whereas this one over here would be 1/2 m times 2v squared. You notice that and that are not the same. M and v don't have equal importance. The v is more important with the kinetic energy, whereas for momentum they have equal importance. You notice here we have to square the 2, here we don't square the 2. So for this to happen, this would have to have twice as much energy afterwards as it did before, right here. And that can never happen. That's why that never happens. So what has to be conserved here is both energy and momentum, right here. Well, what happens if I drop 3 of them? I don't even have 3 of them over there. Well, it borrows one. Again, momentum and energy are both conserved right here. What happens if I drop one of them, but I somehow glued these last 2 together? If I glued those 2 together, then what would happen when this thing came in? This would go off slow, but this would recoil back again. Why? Because you're running into something bigger than yourself, and so you'd bounce back, and it wouldn't look very good. What if we drop 4 of them right here? Again, it borrows 3 of them right there. Or we could even drop all 5 right here, same thing right there. So, or we could drop 2 and 1, they should just swap right there. Or how about 3 and 2 right there, so on. So this is a nice symmetric. If you made them with different sizes, it wouldn't have all that symmetry. People wouldn't like it as much right here. So this is called Newton's Cradle right here. So I just wanted to bring that up right here. Okay, but what I wanted to talk about, also something else they introduced in this chapter 8, and that is this definition of center of mass. Center of mass is always defined as the center of an object right here. So if the center of the object is somewhere, I'm assuming it's somewhere in the middle right there, wherever the balance point is, that's defined as the center of mass. So you can always determine it. Now there's an equation that gives you the center of mass for discrete points. That's the only one we care about. For discrete points, the x position of the center of mass, we define it as the sum of x sub I, m sub I, all over the sum of the m's right here. This is the same way you average almost everything. It's, what do you do when you're averaging numbers? You add them up and divide by how many there are. This is kind of the similar but you're weighting each number by its mass right here. And we also have the y center of mass, which is the sum of y sub I, m sub I, all over the sum of m sub I. So if I just had, say I have some points on an xy axis, xy, let's say you have 3 points. I have a point here, let's say, there's the point, that point is at 2, 1, and let's say its mass is m. And let's say we have another point, let's say minus 1, 1, 2, 3, 4, 1, 4, minus 1, minus 1, 4. Let's make that 3m. And let's say we have a third mass here. Let's put it down in this quadrant. Minus 2, minus 3. 1, 2, 3, right there. And let's say that mass is 5m. And that's at minus 2, minus 3. And we say where, if this were on a sheet of paper and these were the weights, where, or a board, where would the balance point be that would keep this thing balanced right here? And so if I had to guess, you know, it's inside this triangle, and since this is a lot heavier than that, it's probably more toward the 5m side. But you also got a 3m side. So I would probably, you know, if I had to guess, I'd probably guess somewhere in that region is the center of mass, but we could figure it out from this equation right here. The x center of mass, just plugging in, you got the sum of the x's times the m. So this is 2 times m plus minus 1 times 3m, minus 1 times 3m, just plus 5, or minus 2 times 5m, minus 2 times 5m, divided by the sum of all the masses, 5m plus m plus 3m, 5m plus m plus 3m. Okay, all the m's are gone. There shouldn't be any m's left, right? So we got 2 minus 3 minus 10 all over 5 plus 1 plus 3. That's 9. So this is 2 minus 13 all over 9, which is minus 11 ninths. Which is a little bit more than minus 1, which would be, you know, that would be like right along, somewhere along this line right here is the x center of mass. Now if we wanted to get the y center of mass, we could just plug in to this one right here. The y center of mass is equal to, we just do the same thing, we pick the y value. So it's 1 times m times, or 1 times m, plus 4 times 3m, 4 times 3m, plus minus 3 times 5m, minus 3 times 5m, divided by the sum of the masses, which we already knew was 9m. So the m's, again, all drop out, and we get 1 plus 12 minus 15 all over 9. That's 13 minus 15, which is minus 2 ninths. Minus 2 ninths is slightly lower than 0, so minus 2 ninths is about right there. And so there is the center of mass right there. So we can find the center of mass for a collection of points right here. Now you might ask, why did they bring it up in this chapter on momentum right here? Well, you notice if you have, let's say we have a bomb and it explodes right here, and it explodes into all these pieces that go flying out. What did we say? We said that momentum had to be conserved, and the momentum of the bomb before the explosion was 0. So if you add up all these momentums, you also get 0 right here. You can't have a bomb where all the pieces fly out one way right here. If we look at the center of mass right here, you notice all the forces here are all internal. They're all pushing against each other right here. Internal forces do not affect the center of mass. So the center of mass before it exploded was right there. And now if you were to take a snapshot of all the pieces at some later time and say, where's the center of mass? It would still be there. It would always stay there, as long as there's no external forces right here. But on one of your questions on your homework right here, I'm just looking for my eraser right here. Eraser right there. You had a problem on the homework where you had a projectile went flying up in the air. Right here, it was shot out at some angle theta, at some v naught. And then when it got to its highest point, it exploded. It exploded into two pieces. One of them was 1/4 the mass, and the other one was 3/4. I guess I'm not sure if those are exact same numbers, but it's something like that. 3/4 the mass, and 1/4 right here. And it exploded so that this one came straight back at the same speed it was going forward right here. So whatever speed it went, it was coming back. So where's it going to do? It's going to come back and hit the person that shot it right here. It's called karma right here. And then this other piece is really going to go flying way out right here because it was a small piece. And they had asked, what is this total distance right here? This big D right there. Now, one way you could have worked this thing out is you could have worked then the projectile from here all the way up to there. We did that on the test, our first test right here. Calculated the speed right here. And then you could have said use momentum right there. And we could have calculated from these two, since you know this speed and that speed's the same, you could calculate this speed. And then from this speed, you could go back to constant acceleration and calculate the total distance. Add up this distance plus this distance, and that's how far it goes. But there was actually a much easier way of working it out right here. It was much easier. That is, the explosion here didn't affect the center of mass right here. So if this thing didn't explode, if it didn't explode, it would have gone like this right here, and it would have hit right there. Well, the explosion, then the center of mass would have followed this line right here. Well, even with it exploding, when this one's over here, this part is over here, but the center of mass still follows this line right here. So when this piece, this 3/4 m, hit here, the little 1/4 m was way out there. 1/4 m was way out there, and you could get, and this distance, because you could get that distance because that's what it would be as if it didn't explode right here. And we did that in chapter 3. So you could get D right there. So you know where the center of mass is, and you know where one of the particles is. It came back to here. So if you know where one of the particles is and you know where the center of mass is, you could get the x position of the second one all in one step. And so it made it a lot easier right here. Okay, we also had, so this will make this problem a lot easier if you think about it with the center of mass. We had another one where we had someone on a canoe, a lady walking on a canoe right here. So we had a canoe. She was like standing right there. And she starts walking across the canoe. When she walks this way, the canoe has to go the other way, because when she picks up momentum this way, the canoe's got to pick up the same momentum in the other direction. But instead of looking at this from momentum point of view, as she walks this way and the canoe moves this way, the center of mass stays the same. So we know the middle of the canoe was right there, and we know that her mass, I'm just looking at the x position, was somewhere there, and so the center of mass is somewhere in between. So there's the center of mass. Now we could calculate that center of mass, because I'll just put my origin here, right there. And so if we come back and we plug in our x center of mass equation, which is the sum of x sub I, m sub I, all over the sum of m sub I. If I put my origin right there, I'm putting it right at the center of mass, so this must be 0 then, right here. I'm putting my origin right there. If this is 0, that must mean the numerator is 0. I don't even care about the denominator. So that means that this x value, call that x1, times the mass of the canoe, plus this x value, but if this is the origin, this is a negative x value, so we could say minus x2 times the mass of the woman. That should equal 0 right there. So I'm just plugging in this right here, where the x value of one of them is plus x1. This is really a negative x2 because it's in the negative direction. So you have this, but you also know that x1 plus x2, they gave you that distance, 3/2. Okay, so from these two equations, two unknowns, you could solve for x1 and x2. So you could get x1 and x2. Now she walks over to here, the canoe moves back, and so now it's going to look more like, this. She's over here. There's the middle of the canoe over here. But the center of mass is still in the same spot. And so you can do the same thing that you did right here. You could call this, say, x3, and call this x4. x3 times the mass of the woman should be x4 times this distance. And you also know the sum of these two distances because they gave you that. It happened to be the same as this distance right here. So you could find x3 and x4, and they asked, how far did the canoe move? Well, if we just look at the canoe, the middle of the canoe went from there all the way to there. So it moved over x1 plus x4. So they're bringing up this center of mass because it makes it easier to solve certain problems, because when momentum is conserved like this and all the forces are internal, it doesn't affect the center of mass. Only external forces do, right? That projectile problem, the external force of gravity moved to the center of mass in a projectile, but if there was no gravity, it wouldn't have moved right here. So in this case here, this center of mass just stays in the same spot. Okay, so it just helps you with the last two problems.